start, I suppose. So it's my pleasure to introduce Brian Grajales from University of Pamplona in Colombia, who will talk about geodesic on adjoint orbits on a quotient of the special linear group over R. So Brian, you have 45 minutes plus 5 minutes of questions. So thank you very much for accepting to give a talk in our workshop.
Okay, Duan, I want to thank the organizers for the opportunity. For me, it's an honor to be here talking about my research. And thank to the assistants too. So I'm gonna talk about geodesics. This is a topic about geometry, but at the end of the talk, I am going to talk about some issues of analysis that we can apply here. Okay. So I want to say I'm sorry for my English because it is not the best. I think it's not good, but I am going to try to make me understand. Okay. If you have any question or you have any observation, you can talk in any moment of the talk and tell me about that, please. I appreciate that. So this is a joint work I made with Rafaela Prado and Lino Grama. They are researchers from Brazil. And I think this is very interesting because we worked with homogeneous spaces with invariant metrics. When you have an invariant metric, essentially you are working with algebra, with the Lie algebra. All the geometry of the manifold is in the Lie algebra. Okay? But when you consider adjoint orbits, this homogeneous space, we can provide this homogeneous space with a Riemannian metric, which is not invariant, but invariant by the action of a maximal compact subgroup. So when you have only a metric invariant by the action of a maximal compact subgroup, the geometry is different because you can solve all the geometry of the manifold from the Lie algebra. You have to do something else. You have to try to deal with differential equations and with analysis. Okay, then I am going to talk about that later. Okay, first, that is the organization of the talk. I am going to do an introduction of the topics. I'm going to talk about adjoint orbits, how to describe what is that. What is this? And I am going to talk about, I am going to do a construction of the tangent bundle of a homogeneous space with discrete isotropy. Yes, okay, we know that a homogeneous space is essentially a quotient of Lie groups. So when you consider that the subgroup is discrete, you have a beautiful description of its tangent bundle. So I'm gonna talk about that. Then I am going to talk about maximal Fleck manifolds of type A. Okay, and this is a particular case of a homogeneous space with discrete isotropy. We're gonna describe the metrics, the invariant metrics here. And we are going to see that the tangent bundle of a homogeneous space is essentially the adjoint orbits we are going to describe here. Okay, and at the end of the talk, I am going to do an example on the tangent bundle of RP1. This is an example of a maximal Fleck manifold of type A. Okay. So in this case, we have the tangent bundle is a one-sheeted hyperbola. And we have a nice description of the geodesics, okay? So let's begin. First, I am going to put all in context, okay? We are going to consider a non-compact simple Lie group G. And we are going to consider a H0, a regular element in the Cartan subalgebra, okay? In the Cartan subalgebra of the Lie group. I'm going to denote by G, okay? And then, essentially, what is an adjoint orbit? We are going to take the orbit of a regular element in the Cartan subalgebra by the adjoint action of G. This is this manifold. This manifold, we are going to see that is diffeomorphic to the tangent bundle of this manifold, where K is the maximal compact subgroup of G, okay? We have a non-compact simple Lie group, and we have the maximal compact subgroup. Then this manifold, the tangent bundle of this manifold is essentially the adjoint orbit of H0, okay? And then if we consider here that this manifold is a, can you see my mouse?
Yes, we can see.
Okay. Okay. If you consider this manifold, this is a flag manifold. This is a homogeneous space. Okay, so you can talk about invariant methods here. And if you consider, you know that when you have a metric, a Riemannian metric on a manifold, you can extend to the tangent bundle with the Sasaki associated metric. Okay, so we are going to consider an invariant metric here, and the induced Sasaki metric here in the tangent bundle, or in the adjoint orbit. Okay, and then we have what I said. I have a metric that is not J invariant, but K invariant. Okay, that is the first context. Then how can we construct adjoint orbits, and how can we see the identification with homogeneous space and else? First, we are going to consider the same non-compact semi-simple. It doesn't have to be simple with its corresponding Lie algebra. And we are going to fix Iwasawa decomposition with its corresponding global decomposition. Okay, so this subalgebra is an abelian subalgebra. We can fix a set of roots of this subalgebra. We can set a set of positive roots. That's Lie theory. You know how to construct that, and a set of simple roots. Okay, and we are going to denote the corresponding well chamber or Weil chamber of this set of positive roots by A plus. Okay, so how can we construct parabolic subalgebras of this algebra, or parabolic subgroups of these groups? The parabolic subalgebras of this algebra are parameterized by subsets of a simple set of roots. For every theta containing sigma, we can associate a parabolic subalgebra. And every parabolic subalgebra can be constructed like this. Okay, so what is a flag manifold? The flag manifold is to take the Lie group G and take the quotient by a parabolic subgroup. Or so a flag manifold is parameterized by these subsets of sigma. So what we are going to do here is to take theta as the empty set. When you have the empty set, you have P theta is P empty set, and that is the maximal flag manifold. Okay. So we can work with this representation, but in fact, this subgroup, this compact subgroup, acts transitively on the flag manifold. So we can identify this quotient with a quotient of compact groups, K over K theta, where K theta is the intersection of K and P theta, okay? And this is diffeomorphic to the adjoint orbit of an element in the closure of the way of the Weil chamber associated, okay? This, I am not going to do details about this, but this is true and this is easy to see, okay? That is done. So we have that a flag manifold can be seen as a quotient of a non-compact group over a parabolic subgroup, or as a quotient of the maximal compact subgroup with this K theta, or as the adjoint orbit of an element here. And this representation is easier to deal with it, okay? Because the compactness have good properties for us. So to study invariant geometry in flag manifolds, it is useful to use this representation, okay? And that's what we did before, okay? Now, we are going to see that the tangent bundle of this can be identified with this, okay? Then we have the first theorem. I'm going to give the references at the end of the talk. The adjoint orbit of this element, this same element here, is diffeomorphic to this quotient, where z theta is the elements of G that fix this element, this H theta, okay? But the theorem that the demonstration is there. The interesting is that this adjoint orbit, that is a homogeneous space, is also a vector bundle over this flag and is isomorphic, in fact, diffeomorphic to this, well, isomorphic as a vector bundle to the tangent bundle of the flag. So we have the flag that is a homogeneous space and its tangent bundle that is also a homogeneous space, okay? And that is the set of the orbit of an element, okay? So this construction is pretty simple and it's important for what we are going to do here, okay? Oh, sorry. Okay. Okay. So now we are going to describe the tangent bundle, a homogeneous space with discrete isotropy. Okay. So we are going to consider, I mean, this is general. This is it is not necessary for M to be a flag manifold, but a homogeneous space, reductive homogeneous space. We are going to consider a reductive homogeneous space M, that is a quotient of Lie groups. And we are going to consider the case where H is a discrete subgroup of G, okay? Then, in this case, we have a nice description of the tangent bundle. What we are going to do is to consider a semi-direct product of the Lie algebra of G with the same group, see? But the semi-direct with respect to the representation, the adjoint representation of the group. here we are considering this G as an abelian group, okay? And this G as a Lie group. So we have a semi-direct product of Lie groups, okay? And we are going to, we are considering the semi-direct product induced by the adjoint representation, okay? So if you make counts, you can see that this is the product here in the group. So G, I don't know how to say this. This G is this semi-direct product with this operation, okay? Let us fix some things. For A in G and P in M, we are going to consider two functions, two maps. Phi or phi sub A, that is simply, this is simply fixing one of the variables in the action. So phi sub A is simply fix A and considering the action of A in X, in M. You know, I didn't say that, but this dot is denoting the action. The action, you know, you have a homogeneous space, you have a transitive action from G over M. So the action is here, okay? Phi sub P is defined analogously, okay? And we are going to assume that phi sub P is absolute immersion. So what we are going to do is to see how the tangent bundle of this manifold is also a homogeneous space, and the fact that H is discrete will imply that this manifold is parallelizable. We're going to see that. Okay, I'm fixing just the notation. Consider the tangent bundle of M. P is pi is the projection, and for every x in the Lie algebra, we are going to consider this field, this vector field. This is a vector field over N. Okay. Then what we have a transitive action from G, from this semi-direct product over the tangent bundle. I introduced these maps just to define this map, okay? Because this map is a transitive action and its isotropy is this semi-direct product, 0 semi-direct product with H, okay? So, as we know, if we have a transitive and effective action, we have that the tangent bundle, this set, can be identified with the group which is acting over it over its isotropy, okay? Isotropy of the action. So this tangent bundle is also a homogeneous space, and we can prove that this homogeneous space is diffeomorphic also to the Lie algebra times the manifold. So this diffeomorphism implies that the manifold is parallelizable. So you have an homogeneous space with discrete isotropy. You have that its tangent bundle is trivial and is parallelizable. No, it's the same thing, okay? So what we can do here is to consider a particular case. I deal with flag manifold, so I wanted to apply this in our case. Why? Because we have that in the case of a real flag manifolds that is different for complex flag manifolds, the isotropy subgroup when you take the empty set, the parabolic subalgebra induced by the empty set, this subgroup is discrete. Okay. So what we got? We got the homogeneous space, the flag manifolds, a special linear group of dimension n over R over the parabolic subgroup induced by the empty set. This is a flag manifold of type A, and the maximal compulsive group of this group, special linear group, is the special orthogonal group. Okay, this acts transitively here, so we know that this flag manifold can be seen as SON over this group. This subgroup is simply to take plus minus 1 in the diagonal, okay? And the determinant has to be 1, okay? Has to be equal to 1. So this manifold, this flag manifold, we describe in I'm going to give the reference later, but we describe the metrics here, the invariant metrics here. And now I'm going to tell you how is that. We consider this set. This set is a basis for the Lie algebra of SOM. The set is given by these matrices, where the matrix Ij is simply the real matrix of order n, with 1 in the entry Ij and 0 elsewhere. Okay, so this is a basis, and in the article, I'm going to give you the reference. This article, this one, it is published now. In this article, we describe how the metrics are, how the Riemannian invariant metrics are here. And it's pretty simple. You have this basis, and it is an orthogonal basis of this. And all the invariant metrics are given by this quantity, this number of parameters, of positive parameters, where the metric satisfy this. An invariant metric G is simply to take these vectors, these matrices, as an orthogonal basis. And here is the norm, well, the square of the norm of everyone. I want to say something here, because I'm saying that every metric is of this form, but that is not true at all. Because when you have a, I don't remember, I think that for n equals to 4, you have other type of metrics. These are all diagonal metrics, but for the case n equals to 4, you have in the isotropy representation, you have equivalent summands. So you have metrics that are not diagonal. So here are not all the metrics, but just in that case, you have when n is equal to 4, you have all the metrics described here, okay? But we are considering metrics like this, okay? So we have the flag manifold provided with this metric. Then, as we saw, the tangent bundle of this manifold can be is trivial, and is diffeomorphic to this. It is essentially this proposition. Okay. So we have a nice description of how are the tangent bundle of this flag, of this specific flag. Okay. Now, again. Okay. Okay. Then we are going to do what we said, that is provide a F empty set with the flag manifold with the Sasaki metric induced by this metric. And we have this proposition that provide necessary and sufficient conditions for a curve in the tangent bundle to be a geodesic. Okay, so we have here a system of differential equations, and we can note that if you have the tangent bundle, you can consider curves on the tangent bundle can be seen as vector fields along curves in the basis manifold. Okay, so we are going to use that. Curves on the tangent bundles can be understand as vector fields over the projection curve. Okay,
so Brian, I have a question
okay.
about the proposition. So zeta of t is the composition of p with the gamma. Yes, gamma is your geodesic, and pi here is the projection.
Okay, that is, you have gamma, that is a curve on the tangent bundle. Then you project that curve on the basis. You have a curve on the manifold, the flag manifold, and that's what we call a zeta. Okay.
Okay.
And we have necessary and sufficient conditions to a curve gamma to be a geodesic. So we have to study this system of differential equations. Compute these things is too difficult. Is difficult work. I think I tried a lot, and what we are going to tell is what we reached, what we did. But this is not easy. It is not an easy issue. Okay. The first thing is to write a curve in an appropriate way, in an easy way. So you have a curve on the tangent bundle is a tangent vector and its projection. Okay. This is an element on the tangent bundle, the vector field and the projection in the basis. And we can use this identification to see that we can write this in this way. And if we use this thing, we can see a curve on the tangent bundle with this representation. Okay, so what we have here is components that we can study in order to see when this curve is a geodesic or not. Okay, so what we got studying this system of equations, for example, in our case, is the first part was to study geodesics whose projection was a one parameter subgroup of an element of the Lie algebra of the basis. Okay, I am talking about the case when alpha of t is the one parameter subgroup of an element in the Lie algebra. Okay, so this is alpha of t. Then with this description, with this form, we could characterize a horizontal geodesics here. So what we obtained was this system of differential equations. This becomes this, okay? And this system of differential equations, it is not difficult to solve, because our first order differential equation, and okay, you have the parameters, you can do a lot of things, and you can give a lot of examples, a lot of families of geodesics, in this case, horizontal geodesics, in the tangent bundle. I didn't say what a horizontal geodesic is and what a vertical geodesic is, so I'm gonna tell you now. Essentially, when you have this Sasaki metric, you are considering the tangent bundle is to consider a horizontal geodesic would be a geodesic, a curve who is contained in a fiber. You know, you have the basis, you have your fiber, and if you have a straight line in the fiber, that was a vertical geodesic. Imagine you are taking the tangent, the fibers as orthogonal with the tangent space in every point. A horizontal geodesic would be a geodesic who is a vertical geodesic is a geodesic containing a fiber, and a horizontal geodesic can be understood as a vector field who is parallel along its projection. You know, you have a curve on the tangent bundle, and it is a vector field along its projection. If that vector field is parallel, then you have a horizontal geodesic, okay? And we have other type of geodesic that are called obliquous, that are not vertical, not even horizontal, okay? But we are going to study that, vertical, horizontal, and oblique geodesics. So we have a characterization of all the vector fields which are parallel along its projection. By solving this system of equations that can be difficult or hard, more difficult or easier depending on the parameters, you obtain that. You obtain horizontal geodesics. And we also got some results on oblique geodesics. If you write, if we consider again alpha of t as a one parameter subgroup of an element of a Lie algebra, of the Lie algebra, we have that this curve is oblique if the coefficients satisfy this system of differential equations, okay? So these two propositions are proved in the reference to, that is a paper we did with this research, and it is submitted. Now it is submitted. We are waiting for the response. But I want to talk about a particular case when you can see pretty much of these things. The particular case is when you have a RP1, the projective space, real projective space of dimension 1, okay? This RP1 can be obtained as a real flag manifold when you consider the case n equal 2, and you consider the flag manifold, you have a SO2 over SO1 times O1. This is essentially, we can easily see that it is diffeomorphic to the real projective space of dimension 1. And you know that RP1 is diffeomorphic to S1. It's a typical identification that we did. Well, you know that, okay? So how are the invariant metrics here? What is our invariant metrics here in RP1 or in S1? As we saw here, are the invariant metrics over in the flag, on the flag, are given with this equation. So in this case, we have only one element, which is W21, and we have just one parameter. So invariant metrics are identified with R plus, one parameter for the metric. Okay, Then in this case, we have a nice identification with the tangent bundle. This is the proposition, but I'm going to display this with this picture, okay? What you have to do is the following. You have here S1, that is RP1, a flag manifold, and you are going to consider this one sheeted hyperboloid, okay? You know, this hyperboloid is a ruled surface. A ruled surface is a surface that is the union of disjoint straight lines. If you take these straight lines here and you are and you rotate that the straight line, you obtain the hyperboloid, okay? So how you construct your is isomorphism with the tangent bundle. You know, you have here S1, and the tangent bundle is to take all these straight lines tangent to the circle. So you have to take this straight line that is contained in the hyperboloid and do this projection. Okay, construct this projection. So you have a linear isomorphism from this straight line to this straight line. Now do that with all the lines, and you have your isomorphism between this H, this hyperboloid, and the tangent bundle of S1. That's an easy construction, and we can explicitly write this function, write this map, sorry, okay? So here we are saying, well, okay, we are saying how the manifold is diffeomorphic to S1. We need this explicitly because we are going to do some things here. This is the diffeomorphism between the flag manifold and S1 explicitly. And we have that the metric, the invariant metric here induced the metric induced by R2. The canonical metric, Riemannian metric in S1. Okay, well, by a factor, but okay, it's a multiple of the canonical metric. And this isomorphism can be used to describe the geodesics in tangent bundle in this manifold, in this hyperbola. How we do that? You consider a parameterization of the one sheeted hyperboloid, this parameterization, and you are going to see that this parameterization essentially gives us the geodesics, because this parameterization, when we take in the domain straight lines under this parameterization, we can prove that they are transformed in geodesics on the hyperbola. So we can distinguish here three cases. The first one, when you take a horizontal line in this domain, it is transformed in a geodesic here. How are the geodesics in this hyperboloid? Are circles, horizontal circles, okay? So you have this is an horizontal geodesic. This is a horizontal geodesic, and like this are all the horizontal geodesics. Vertical geodesics are easy because are simply these straight lines. The vertical geodesic has they have to be contained in the fibers, so they have to be this straight line. So they are obtained when we consider a vertical line here. you take a vertical line here, you map with your parameterization, and you obtain a geodesic here. So we have a vertical geodesic. And more interesting is the case when you have an oblique geodesic. If you have a line which is not horizontal but not vertical, either vertical, so you have a line here, it is transformed in an oblique geodesic. And how are they? Are like a spiral, but it's a spiral, a weird spiral. It is not the same geometry that we have in the hyperbole when you consider as a submanifold of R3. It is a different geometry, okay? We have a different geometry. So that's nice to see, and that give us ideas or how can we work with this. So well, what I'm going to say now is how can we deal with analysis in these manifolds? When you have a homogeneous space, you know, we can study geometric flows on there. When you consider invariant Riemannian metrics, studying geometric flows, for example, the Ricci flow or others, reduces essentially to solve a system of ODEs, okay? So you have to know something about dynamics or ODEs to study that flow. But in this case, it's different. Why? Because you have metrics that are not invariant. So when you consider geometric flows there, you obtain a system of PDEs, no more a system of ODEs, because the invariance is only over the maximal subgroup of the group G. So you can study Ricci flow here, and you can use a part of Lie theory, but also you have to use other things about analysis or PDEs, because the metric is not invariant in this case. Okay, and that's it. I hope you understand what I want to present here, what I wanted to present here. And again, many thanks for the assistance and for the invitation. Here are the references. Essentially, all I talked here is in this paper that is submitted. And this here is the reference where for some propositions I said before. And thanks. Any questions?
Okay, thank you, Brian, for your very nice thoughts. There is a complexity when working in explicit computations on manifolds that you show. So there are questions for Brian.
I have a question.
Okay.
So, Brian, you were like interested in geodesics, which are like minimal surfaces of dimension 1. Are you also interested, or are you thinking about looking for nice expressions for higher order manifolds, minimal submanifolds? Like dimension 2 maybe, or higher minimal submanifolds? Like in this context of flat manifolds and this like, or I don't know.
I think that is interesting to consider minimal surfaces, but for now I haven't dealt with minimal surfaces. But if we can try to do something similar to this thing we do with flat manifolds. But the difficult is because here we use a lot the Lie algebra of the homogeneous space, you know. So in minimal surfaces, I wouldn't know how to translate that things. I'm not sure if I answered your question, Santiago.
Yeah, thank you.
Yes. Okay.
Okay, thank you, Santiago, for your question. So, other questions for Brian? I have, but myself, a question, Brian. Could you mention something about the complexity of this theorem of classification of where you classify the invariant metrics with this partial differential equation in terms of the projection and in terms of the Levy beta connection?
You're talking about the complexity,
Of the, yes, of the PDE equation that characterize all the invariant metrics with respect to the parabolic subgroup.
Okay. I am not understanding what you want to say when you say complexity. I'm sorry. Complexity
yes,
of the
complexity in making computations, or complexity
okay,
when you
okay,
compute.
Okay, Duan. For me, it's very difficult. For me, because I am not familiar with PDEs. Okay, I am not. I don't know much about that. But that's the idea, because I know how to set the system of PDEs when we want to study a geometric flow, for example. But that's the idea. If I can work with someone who knows about PDEs, we can work together in that, because I know how the PDE is. What we want to do after that is to study properties of that system, and that's when analysis can work with that, you know. But for me, it's very difficult. Maybe for you, it is easier.
We can
Okay.
check, but it looks that it's a very deep analysis that you are doing with the metrics. So yes, and you are using a lot of yes, explicit Lie theory. So it looks very interesting indeed. Okay. There are more questions for Brian. Okay, if not, then thank you very much, Brian, for your very nice talk. That was very inspiring, at least for me. So